Earlier we have seen that there are three types of cases to determine the time required to dry the solid up to the desired extent. One of those three cases were the case number 2, wherein the falling rate period curve of drying is a continuous line. What if this line is not continuous? What if this line is partially continuous and partially a curve? Just like this. For example, from this point, if it is a curve, instead of being a straight line throughout, let there be a curve like this. Now we cannot say that the rate of drying is this. The rate of drying is somewhat different. It's unpredictable. But we can definitely find out the time required to achieve the desired drying along this curve. How? See, for case number 2, earlier it was theta f is equal to s divided by arc into xc minus x star into ln of x1 minus x star upon x2 minus x star. We got this relation because we were having this relation. For r, we were having rc into this term. But now the case is different. Here there is no specific r. There is definitely r versus x data. That is the rate of drying versus the moisture content of the wet solid. We may have this data, but we do not have the specific r for such kind of curves, for such kind of drying curves. So how to determine the time then in such a scenario? Very simple. We were having this equation. Theta is equal to s divided by a multiplied by this integral term. Here in this case there is no specific r, but we have the data r versus x. So let us erase this derivation. Now theta for such a case is now, this all will go. This all will go. Maybe this is xc, this is x1, this is x2, and this is x star. Here C to D, it's a continuous straight line, and from D to x star, it's the curve. In such a scenario, there is no specific R, but there is definitely RC. But we have to find out the time required to dry a wet solid along the falling rate period. Theta is equal to S divided by A into x2, x1, dx from R. We would be having S, that is the dry weight of the solid. A is the surface area exposed to drying medium, maybe air or any gas. Surface area. Dx is the moisture removed from x1 to x2, and R is the rate of drying. We do not have specific R, so we cannot solve this. But we can definitely draw one curve. And the curve is 1 divided by R versus X. What is that curve? 1 divided by R versus X. We would have been provided with R versus X data. From that data, we have to draw a curve, a drying curve. For such a case, we have to draw 1 by R versus X, not R versus X. Because here R is in reciprocal form. It can be written as 1 by R into dx. So, this integral can be solved over this curve. How? The integral of this integration between the limit x2 to x1 can be got on this curve. How? x1 is the initial moisture content and x2 is the final moisture content. And we have drawn this moisture content versus 1 by R. Whatever curve we get in this way, the area under this curve, the hashed area, that area under the curve will give us this integral, the value of this integral. So once we get the area under the curve, this area under the curve has to be put in place of this integral part. And this integral part multiplied by s divided by a will give you theta, the value of theta. When this equation is applicable and there is no specific R for such kind of drying curve, it's partially continuous and partially a curve, right? So that is the way to determine the drying time for case number 2 with the falling erect period curve partially continuous and partially curved. Thank you.